All right, hello everyone. Thank you for coming today. I want to start, of course, by thanking also the organizers for having me. It's a great pleasure to be here today and having this opportunity to visit campus and learning about what everyone else is doing. So today I want to talk about neural network quantum states, but from a different angle. Instead of focusing on calculating ground states, I'm going to focus on calculating spectral functions and thermodynamics, which is something that I think we haven't heard of in this program yet. So the work has been done mainly by a great group of students and postdocs. Well, basically, mainly by Doug. Doug Henry is now at Giuseppe Carleo's group at EPFL. Honwei is now at Microsoft, making like 3 times my salary. And Philip is at QERA, probably making twice my salary. And the work that I'm going to present has been published in this list of references here. And I can share them with you if you're interested. But I'm going to show them when relevant during the talk. Okay. I'm going to start by motivating my talk in a similar way as Antoine did yesterday. The main reason why we're interested in variational Monte Carlo and neural network quantum states as variational estimators for ground states is that in strongly correlated systems, and in particular in this case, frustrating magnets, there is a large number of competing phases at very low energy. And it's very hard to distinguish one phase from another, which one wins over the other. And this may depend on many things, actually. They're so close in energy that you may just change the aspect ratio of the lattice, or whether you work on a cylinder with open boundary conditions or in a torus with periodic boundary conditions, you get different ground states. And that's illustrated here in this plot, for instance, for the Kagome lattice. Oops. This will work, but I think this is more or less the state of the affairs right now. You have, DMRG is basically the state of the art in this area, but you can see that many DMRG works give different competing ground states. It's not clear which one is the actual ground state. Well, right now, the consensus is that it's a spin liquid, and I think that's pretty much accepted. And another example is the J1, J2 model, which has been around forever since I was a student, like, I don't know, 30 years ago, when Phil Anderson proposed that this could be a good representation of cuprate superconductors in the multi-insulating state, we have, of course, different values of J2, competing states. Small J2, we have an antiferromagnet. Large J2, we have a striped or columnar phase, and that's well understood. They break SU2 symmetry, and they have a conventional sort of magnetic order. But in the middle, in between, we have a region of parameters where it's not clear what's happening. And it's being speculated that this is a quantum spin liquid, but most recent state-of-the-art work suggests that it's actually a plaquette order. Now, something curious about this slide is that if you notice the authors of the first work, Hong Cheng was Donna Shang's postdoc, and Leon Valens was Matthew Fisher's student. So I don't know what's going on here. All right. So you heard a lot about neural network quantum states. I'm just going to refresh your memory because I want to show you the bag of tricks that we use. Of course, the problem we have is how to represent a complex many-body wave function. And so in this case, I'm going to focus on spin systems. So my configurations are just spin configurations. And we want to parameterize these coefficients. We have, say, of the order of 2 to the n coefficients by a smaller set of parameters. So we want to basically postulate that there is some magic black box that takes spin configuration as an input and spits out the coefficient of the wave function for that spin configuration. And this black box has a lot of knobs that are our variational parameters that I refer to as alphas. And now what we have to do is find the best alphas that give you the best wave function that approximates the ground state. And this becomes an optimization problem, but it's also a compression problem if you think about it in terms of information, because what we're trying to do is get a wave function that is, say, we can think of it in terms of image processing, like, our raw image is our ground state, what we're looking for, and what we're doing is approximating this ground state by some compressed form, let's say JPEG, GIF, PNG, and this, of course, is going to be a little. We're going to lose resolution when we do that. Our hope is that we can achieve lossless compression. That means that we can actually preserve all the information of the ground state, even after compressing the information into this black box in terms of these parameters alpha. And another way to say it is in terms of representability. We can think that our ground state lives on this large Hilbert space, and we have a manifold of variational states that can be represented by this black box that live in a sort of subspace of this full Hilbert space. And in reality, the picture that I have in mind, at least, is that this manifold is more like this. It's just like percolates through the Hilbert space. And what we're trying to do is to make this mesh as dense as possible, such that you can arbitrarily approximate any quantum many-body state as accurate as possible. An example of variational states, of course, is the Jastrow wave function. In this case, we postulate a mathematical form for the coefficients, which is very simple. It's just an exponential of the spin correlations. And surprisingly, this is very accurate, or relatively quite accurate for spin systems. And, but it's not the state of the art. But this is a good pedagogical example. Another example is matrix product states, which are basically the engine of the density matrix normalization group, which is under the hood. And basically, the DMRG is nothing else but the optimization of a variational state of this form, which is a product of several matrices. And all the information is encoded in the coefficients of this matrix. Let's say in the context of neural network quantum states, I guess the first paradigm that was put forward by Carleo and Troyer was the RBM, the restricted bottom machine, which is probably the simplest neural network architecture you can think of. And this is going to be our fruit fly or C. elegans for the rest of this talk. We're going to use the simplest possible model here because we are mostly interested in trying to see how we can use these states to, again, represent thermal states and spectral functions, and we're not so interested in just getting state-of-the-art energies. Right? So nowadays we hear a lot about transformer neural networks and others, and I'm just going to stick to this one for illustration purposes. The variational solution, we know it's obtained by minimizing the variational energy using quantum Monte Carlo, or variational Monte Carlo, rather. And I want to spend a couple of slides explaining how we do the variational optimization. Everybody, I mean, most of you know, but this is going to be useful when I show how we do spectral functions. So one way, of course, the naive, more straightforward way to do it is using variation gradient descent. You just calculate the derivatives of the energy with respect to your variational parameters, and these act as sort of like forces that drive you towards the minimum, and but this is prone to getting stuck on metastable states or to just have very poor convergence. So the state of the art is the natural gradient descent or stochastic reconfiguration that in the context of quantum or variational Monte Carlo was first proposed by Sandro Sorella, and but even though it was known as natural gradient descent in the machine learning community. So the idea now is not to sort of approximate the energy. I'll just do it intuitively without going into the equations. The idea is not to just minimize the energy, but what we are trying to do is to get as close as possible to the optimal solution. So we do it by measuring the distance to the exact ground state in terms of the Fisher information. And the Fisher information is nothing else but the measure of the distance in terms of an angle. So you can think of psi as being my true ground state and phi as my variational solution. And what I'm trying to do is to minimize the angle between the two. So the distance is measured in terms of angles, and I don't care about the magnitude or the normalization because this is quantum mechanics. So the normalization, you know, is not important. So this method relies again on calculating these energy derivatives, but also on calculating this correlator. This is the so this matrix SKL is basically this correlation function between two operators that are defined as basically the log derivatives of your variational wave function with respect to the variational parameters. And the good thing about this approach is that when you have some sort of variational principle or you're trying to approximate a known state and you don't, you cannot rely on just minimizing an energy, this approach gives you the means to postulate a sort of minimization procedure to converge to that state. Another way to see a stochastic gradient descent is in terms of imaginary time evolution. This is how Sorella proposed it originally. So the idea is that you are doing evolution in imaginary time. As you do evolution in imaginary time, basically you hit your wave function with the Hamiltonian, and when you do it many, many times, eventually you're expected to converge to the ground state as long as you have some overlap with it. And so this can be postulated in terms of minimizing this energy, this distance again, that is evaluated in terms of the Fauvéni study metric. And when you do this projection, what you're trying to do is you're trying to guarantee that your every time you hit the Hamiltonian, basically this is illustrated here, every time you hit your Hamiltonian, imagine your variational states live on this manifold M. These are all the wave functions that can be parameterized by these variational parameters alpha. And when you hit it with a Hamiltonian, your new state doesn't live on this manifold. Basically, you kick it out of the manifold. And what you have to do is you have to project it back into the manifold. So this is called evolution in the tangent space. And what you're hoping is that the trajectory of your state in the tangent space or along this manifold is going to be the same as, it's going to represent the trajectory in the full Hilbert space, as close as possible. And that eventually you're going to converge again to the best representation of the ground state. Some tricks that we use, we use translational symmetry and all the point group symmetries of the lattice. That means that we take our RVM and we basically apply all the point group operations on it, and we average. And when you do this, since the new wave function is just a sum, it's a sum of RVMs, it's no longer an RVM. So the idea is that it doesn't live on the manifold of just plain vanilla RVMs anymore. It increases the representation power of it. Another trick that we use is this Langshus recursion that, unsurprisingly, was also proposed by Sorella. And the idea is that, imagine you have your variational wave function, your neural network quantum state. You hit it with the Hamiltonian, and you get a new state, and you can repeat this procedure. And you do basically Krylov expansion. And what you have to do is an orthogonalization. And you can build a tri-diagonal matrix with these states and diagonalize it. And when you do that, you get a new estimate of the ground state that is better than the original estimate. So in reality, you don't need to calculate these states. So this is, we actually only do 1 or 2 steps because of the accuracy that you can gain is very, very tiny, and it's already affected by your numerical error. And so what you do is you don't evaluate the new state. You just evaluate these matrix elements. Yes. These matrix elements here are easy to evaluate, and basically just get the new energy by analytically diagonalizing the 2x2 matrix. And to give you an idea of how accurate this is, I'm showing you here what at the time, we're talking 2022, were state-of-the-art results. This was before vision transformers and etc. So this is for the J1, J2 model. You see that convolutional neural networks will give you this energy in blue as a function of J2. RBMs, just plain vanilla RBMs, will give you this black line when you use all the, sorry, no, these are, yeah. This is when you use all the symmetries. And RBMs, after you apply Langshus for a couple of steps, gives you these red dots here. And as you can see, at the time, it wasn't obvious to me why you had to use convolutional neural networks or super duper architectures with zillions of variational states if RBMs gave you this kind of performance. So in a nutshell, I'm not saying that we don't need to improve. What I'm saying is that maybe we are, brute force is not the way to go. Maybe there are other models that are maybe simpler and that somehow have a more physical intuition, let's say, about what's happening in the quantum many-body wave function. So this shows here this is for a 6x6 lattice, so we can do exact analyzation. And here I'm comparing also to 6x6. I cannot read which is the exact results because I'm also showing 8x8 and 10x10. No, 6x6 and 10x10. And you see that our results and results from other methods agree very well. But sometimes you have to look at the numbers, and you see that here that the accuracy and the energy is basically in the 7th digit, which is quite good if you ask me. Now, I promised that I would talk about thermodynamics and spectral functions, so I'm switching gears, and now I'm going to talk about thermodynamics. So there are the motivation, yes?
Can I briefly ask about the previous slide?
Sure.
these larger transformers, like surely they can get maybe lower energies, but does that matter for the physics that you study, or could you do the exact same thing?
It does matter in this spin liquid region right here, where these curves cross. Clearly, these system sizes, first, if you stare at it like this, these curves won't tell you anything. You have to do a finite size scaling and an analysis of the correlations more carefully. But but yes, in this region, you want to convert, to the lowest possible energy as accurate as possible, because you have all these competing phases.
But I'm asking, did this vision transformer, would they have been able to draw different conclusions than you?
I'm not drawing any physical conclusions from this work.
Okay.
I'm just showing energies.
Yeah.
I didn't want to get into to that controversy. Yes?
Question about the Lanczos recursion.
Yeah.
So do you find that with more expressive networks that it does less? Because it seems like the Lanczos recursion, if you measure time function, very similar, should give you similar spectral information. And it's surprising to me that you would get anything new out of Lanczos.
So first, you do imaginary time evolution or stochastic gradient descent to converge to the best possible RBM. And then, once you did that, you apply the Lanczos steps. And now you're going to get a linear combination of RBMs, which have more expressivity than just a single RBM, right? So if you think if you not think like that, huh?
Is the Hamiltonian applied to your no level quantum state still another no quantum state right?
It's not. It's not. But so you don't have to calculate the new state. You only need to calculate the matrix elements. So that simplifies things. You don't need to do the projection.
That suggests that your no quantum states are not so close to the ground state. There's some extra gap.
Yes, you can still improve. It's in, somewhat similar to what Shiwei showed yesterday, where he did the first variation of Monte Carlo and then diffusion Monte Carlo on top of that. Right? So here we're doing variation of Monte Carlo, and then we're doing the Lanczos steps. All right. Yep.
This Lanczos step, can you do more than 2 states?
Yeah. Well, 3, but yeah, but the easiest way is to do one Lanczos step, and you get. Well, in that case, yes, you need to, exactly how my student did it, it escapes me. So, but you can do more than 2 Lanczos steps. So actually, this result is for 2 Lanczos steps. So, yeah, Liang?
In BMC, you comment on 2 methods which get exact states.
When you do Lanczos, you're saying you don't get just one eigenvalue, you get 2, so you can get a gap, or is that what you're trying to say? Huh?
Just one general question. You talk about BMC, you combine the variation of energy to get all states.
Right.
Are there good methods to get the exact states, low-lying exact states?
I'm going to show you how to calculate spectral functions, but extracting the exact energy of the excited state from there is not obvious. But maybe you can extract gaps if you have enough accuracy. But one way to do it with to extract excited state energies is by using translational symmetry. So you can get the ground state energy for each momentum k, and then you get the low-lying spectrum. Yeah. All right. So my inspiration to do this work comes from the DMRG literature, because I grew up doing DMRG basically, and the same way you guys are growing up doing machine learning, and the two approaches, well, there are more than two approaches in the literature. One is just you work with the with the density matrix, with the thermal density matrix, and you evolve it in imaginary time, starting from infinite temperature. What I'm going to do is actually more closely related to these two proposals. One is METS, minimally entangled typical thermal states, which is a way to do it matrix per states. And the other one is this canonical thermal pure quantum states, which is a way that was proposed to by a Japanese group to do it with ED. And the idea is to start from some random product state and just simply evolve it with in imaginary time with h/2 instead of h. And then you calculate any observable just sandwiching this state. So you just work with pure states. Of course, one random state won't do it. You have to do it with many, many random states, say 100, 200, and then average. That's the idea. So it's fairly straightforward. So the question is, how do you do it in practice? And first you need to define your random states, and we do it by just taking random product states and with coefficients given by some Gaussian distribution. And it turns out that this can be encoded into an RBM very easily. You just use these weights, basically all set to 0 except for these biases. And then we evolve in imaginary time by using stochastic reconfiguration, right? Natural gradient descent. I told you earlier that natural gradient descent is nothing else but evolution in imaginary time, right? So all you have to do is the same you were doing before. Just do natural gradient descent starting from this state, and you get a trajectory in imaginary time. You measure at every time step, and then you do it many, many times over many, many initial states, and you average. It's that simple. And this is what you get. So this is the energy for the plain vanilla Heisenberg model on the square lattice. In this case, we have very accurate results from Anders Sandvik, who did stochastic series expansions, calculations on very large lattices. And we asked him to share the data with us. And this is for 6 by 6, and this is for 8 by 8. And the red line, the surprisingly smooth red line, is our results, and the black dots are stochastic series expansions. And now, the thing is that at high temperatures, things look very, very accurate. At low temperatures, actually, you cannot resolve it in this figure, but there are some discrepancies. Because once you reach the best approximation to your ground state in this variational manifold, your system does not longer evolve. And it gets stuck. So it works to low temperatures, but at some point it breaks down. And that depends on basically the model you use and its representation power. Here, it's very hard to resolve. There are some error bars. The error bars are shaded in gray. But this is the specific heat, which is the derivative of the energy, basically. And you see that things break down around here, like the order of J/2. And but still remarkably accurate. And this is the magnetic susceptibility, which is basically the star correlation function. And you see that the agreement is quite good. It's not awesome, excellent, but quite good. And but the nice thing about this is that it was obtained at a very low computational cost. And we didn't have to basically do anything to our code. We just used our code for calculating ground states, and we just run it many, many times, starting from many, many random initial states. Yes? This is a thing of the order of 100 shots, let's say, 100 initial states. Mm-hmm. But you can run them in parallel on a cluster. So So this is equivalent to 100 ground state calculations. Yeah.
And so do you, I guess you start evolving your state and then you measure
At every time step.
at every time step. So, okay, so you do one, you go from 0 to 4. And then
Yeah, 0 is infinite temperature, right? So in reality, you start from infinite temperature from the far right, and then you evolve it to low temperatures. Yeah.
and do you, how do you choose the time steps? Do you,
Or you have to use a very, very tiny time step to make sure that these curves are smooth and the trajectory doesn't go in random crazy directions. So basically, it's like using a small learning rate. Running rate.
and I guess the larger temperatures may be easier, and then as you get to the smaller ones, yeah.
Oh yeah, it becomes very, very tiny at small temperatures because it's, we are evolving in, 1 over, in beta, right? 1 over t. So it's, yeah, it takes, a lot of time to get here. Okay, I'm switching. Any other questions about thermodynamics? Okay, so again, I'm switching now to spectral functions with variation Monte Carlo, and again, we're using 2 techniques that come from the DMRG literature, but applied to neural network quantum states. And the first one is called correction vector. First, let me define the quantity we're looking for, we're after. So we're trying to approximate the 0 temperature Green's function, which is defined generally like this. Basically, you have your ground state. You hit it with some operator A. Then you evolve it with 1 over h. Z here is basically the frequency you're targeting. And then you hit the state again with a dagger and the ground state. And the spectral function is defined as basically there is something missing here, the imaginary part, so of the Green's function. And we're going to work with our just simple Heisenberg Hamiltonian in 1D because these are proof of concept calculations and we have very accurate results in 1D from DMRG. So for spins, this Green's function is basically a spin-spin correlation, but with this one, the inverse of the Hamiltonian in between. And the way we evaluate this quantity is by introducing 2 auxiliary states. The first auxiliary state, we're going to call it A. It's just the state you obtain by applying this operator to the ground state. So you have the ground state, and you have this state, which is A times the ground state. And then this state, which is 1 over h applied to A. So in reality, we have 3 states. And we need to apply this state psi here, and and we do it by actually solving this equation here, which is z minus h applied to the state we're after is equal to A. And once you find this state, all you have to do is calculate this overlap, and you're done. Now, the catch here, so the crux of the problem is calculating this correction vector. And we do it the following way. Again, we apply natural gradient descent. We want to solve this equation. It's basically a large system of equations, if you will. Basically, we're trying to calculate the inverse of this matrix, in other words. And we do it, again, by using the Feiguin study metric. So we want to calculate the distance between the target state and A and z minus h times the correction vector. And basically, if you do all the math, you end up with some sort of equation of motion for your variational parameters that looks like this. It's very similar to the equation of motion for stochastic reconfiguration for ground state calculations, but now your S matrix that we had before is replaced by, which is your metric tensor, is replaced by this one. And where Q here is just Z minus H. And so we have to measure all these correlators at every step and do stochastic reconfiguration as usual. Now the catch here is that we need to do this for every frequency omega or every value of Z. So if we want the full spectrum, we need to do this for each value of omega. But again, we can run it on a cluster in parallel, and it's not a big problem. Oh, this is repeated. I forgot to remove that. Okay, so this is a benchmark for a short chain with 10 sites, and we thank the referee for suggesting that we show this. In red is our result, and in black the exact result from DMRG, and you cannot really tell the difference. So it's very, very accurate. Yes.
Yeah, so how do you compare your method of computing the spectral function with, let's say, you compute the out of time order parameter and then do the Fourier transform?
I don't know because we haven't done it. So you want to use the time-dependent variational principle to evolve it in real time and then Fourier transform. Yeah, so we haven't done that. Yeah. So we're working directly in the frequency domain. All right, if we want to do the same for larger systems, this is what you get. The first, typically, as it happens for this method, also in DMRG, you get the low-lying states or the low-lying spectral features very well resolved, but at higher energy, you get a lot of noise. And in this particular case, Doug came up with a very smart correction method to improve the correction vector. And actually, to improve the estimates, I'm not going to get into the details because it's quite technical, but you can look at it in our paper. And if you do that, so the results with no correction are in red, but the results with the correction, give you the blue curve that gives you the best approach. Now, if you see it like this as a cut in frequency, you can actually visualize all the sources of error. But if you do it as a color plot, it looks pretty neat, right? So this is the spectrum for a chain of 30 sites. This is a small chain again, but as I mentioned, we are doing proof of concept calculations, and we're not interested in seeing how much we can push the method in terms of system size. So this is the dynamical DMRG, which is doing precisely the same thing, correction vector with DMRG. And these are the results with variational Monte Carlo, with frustration and without frustration. I forget I have the pointer here. So the second approach we tried is using Chebyshev polynomials to expand the spectral function. This may require some time to explain, but in a nutshell, the spectral function, A of omega, now can be expanded in terms of these Chebyshev polynomials T. And these T's can be, well, we know what they are, and they are multiplied by this prefactor mu, and mu is the Chebyshev moment which is nothing else but this correlator, which now we have this polynomial of h instead of 1 over h. And this polynomial of h can be evaluated recursively. Basically, you introduce these vectors, which are, the first one is the vector a we had before. So you apply a to your ground state. And then the next vector, you apply t of n to that state. And your moments are calculated as these overlaps. And this can be done recursively as shown here. And once you do this, you see that it's fairly simple. You have to calculate all these moments, these overlaps, and then plugging them into this expression, you get the spectrum. And the spectrum here is cleaner and more smooth, if you will, because this function that you are plotting is in terms of the polynomials is also smooth, and the error is in the Chebyshev moments. And as you increase the number of moments, the better the resolution, the better resolved the spectrum is. So this is illustrated here, where for 40 moments you get the red smooth curve. For 60, you start seeing these oscillations, and for 100, these oscillations get sharper and sharper, illustrating the discrete nature of the spectrum for this small system size. But and you can do it for many values of momenta, and it works quite well. This is, again, the spectra plotted in momentum and frequency, and you see that it's practically indistinguishable from the DMRG spectrum when you look at it like this. And the thing is that you can do this in 2 dimensions as well. So just for illustration, we did it for 6 by 6. And you see that, again, the low energy peaks get very well resolved, but if you want to go to higher and higher energies, you need more and more Chebyshev polynomials, Chebyshev moments. The error propagates as you go to larger number of moments, and the accuracy suffers a lot. But with this, I want to conclude. The idea is that you can actually use variation Monte Carlo not just for ground states, but you can use it for calculated quantities that are actually experimentally observable, such as spectra and thermodynamic quantities. And this is not restricted to RBMs. You can apply it to any variational form that you prefer. And at the heart of these approaches is just the stochastic reconfiguration method, and basically the limitations are simply the expressivity of your wave function and the computational cost of optimizing it. So it's this can be hopefully pushed to larger system sizes, fermionic systems, and other problems. And with this, I want to thank you very much for your attention, and I'll take your questions.
Are there any additional questions?
Can I ask a question about the correction vector inversion? So does the error in higher moments come from error in the ground state before you iteratively invert, or is it problem to optimization when you iteratively invert?
It's on the inversion of the matrix, yeah. So all the errors come from the inverting the matrix. So
Why is it harder to invert the matrix as you take Z larger?
that's a good question for Doug. I can put you in touch with him. So I believe it's just that you're getting stuck in local minima, and it's hard to get out of there. So metastable solutions, as usually happens for these variational methods. Nothing else.
Lactose corrections on this?
No, you cannot do that here. So for the correction vector method, you just start from your estimate of the ground state, which could be, it could be like, so you're talking about if we do the Langevin projection, the Langevin iterations to calculate the ground state on top of this, huh?
No, when you invert the matrix, you're solving a variational problem.
Right.
And you can do Lactose.
Oh, you can do the continued fraction too. Yeah. We did that. Actually, I believe we compared to panel C here is the continued fraction with RVMs. So it's the same idea. Yeah.
Very nice talk. I have two questions about Cheshire. So the first question is, what's the largest extension order you can reach, and what limits you from getting higher extension order? And also, the second question, maybe we can start with the first one.
So we use up to 100 moments, and basically Doug observed that the accuracy wasn't improving. So he would stop there, but I probably the problem was that the results were dominated by numerical error at that point, and we're just getting worse instead of getting better.
So we are following a work with Cheshire matrix product state, where we try to apply Cheshire to interacting system based on matrix product state. So there's this technique where we can actually try to do linear prediction or time series prediction on top of
Right.
moments. Have you ever considered that?
No, we didn't, but that's a good idea.
Okay, thank you everyone for the questions. Maybe we'll sing.
Oh, yeah, that's okay.
Let's save the, if you have any further questions, please talk to our speaker during the break. I'm here, we'll be happy to answer.
All right.
And let's sing the speaker one more time.
Thank you, everyone.